Welcome to the Dev Journal. Today, we are exploring the messy crossroads where laboratory dreams meet the brutal friction of the real world. As developers rush to turn experimental artificial intelligence into autonomous workers, they are hitting a wall of massive security failures and the crushing weight of operational costs. We will look at a privacy breach so massive it has redefined our understanding of system vulnerabilities, alongside a new multimodal model from Microsoft that claims to master both complex mathematics and graphical user interfaces. Vance, you have been tracking the methods engineers are using to keep these massive models from bankrupting companies.
The financial pressure is real, which is why engineers are obsessing over tiered context loading techniques that could potentially slash token expenses by 76%. I am digging into the underlying architecture to see if they can sustain the scale required for production deployments without sacrificing performance or speed.
Beyond the balance sheets, the stakes for our digital infrastructure have never been quite this high. We are pulling back the curtain on the engineering shifts that will define the next decade of automation. Our first story begins with a catastrophic security failure that has left the entire engineering world reeling. The sheer magnitude of the OpenClaw exposure is staggering when you look at the Schaden analysis from February 2026, which identified 39,221 instances using default credentials or having zero authentication at all, showing a massive gap between rapid developer adoption and enterprise-grade security. This lack of oversight led directly to the catastrophic Moltbook backend breach, where 1.5 million application programming interface tokens were leaked alongside 35,000 email addresses, effectively handing the keys to the kingdom to attackers who can now impersonate users across a vast array of connected services. Even the official ClawHub marketplace has become a minefield, with a recent audit from Snike discovering 341 malicious skills, suggesting that the entire ecosystem is currently a playground for credential harvesters who are exploiting the trust of developers looking for quick automation tools in their daily workflows.
Sloan, the structural negligence underlying these exploits is almost hard to believe when you look at how the Common Vulnerability Scoring System score of 8.8 for common vulnerabilities and exposures 2026, 25.3 allows for remote code execution with zero user interaction, storing integrated service credentials in plaintext JavaScript object notation, files at the home directory.openclaw/config.json path, is a complete disaster that ignores basic operating system level security practices, leaving sensitive authentication keys exposed to any local process or malicious actor on the system. Analysis revealed that 93% of the 42,000 plus publicly exposed OpenClaw instances suffered from critical authentication bypass vulnerabilities, which is not just a minor bug, but a fundamental failure in how the core software handles identity and access management for these high-privilege autonomous agents. The Mac operating system keychain command injection in common vulnerabilities and exposures 2026-27 487 proves the point, because even unsanitized skill names could be weaponized against the host operating system in all versions prior to 3.0.8 to reach into secure storage. We are witnessing a desperate attempt to pivot from the current wreckage of agent security to the new standards being drafted to fix it, because securing root access systems requires a complete rethink of how we permission artificial intelligence to interact with our machines and private data in production environments.
Transitioning from simple code autocomplete to autonomous agentic execution represents a massive leap for the industry. To manage this high-stakes shift, OpenAI launched Codex Security to guide developers through the complexity. It marks a fundamental change in how we perceive the role of artificial intelligence in our everyday development workflows and production environments. Professionalizing this frontier is now a government priority, with the National Institute of Standards and Technology setting a firm deadline of March 9, 2026, for public comments on their upcoming security guidelines. This timeline suggests that the era of the Wild West in agentic systems is finally coming to a close for enterprises. Building genuine trust for large-scale enterprise deployment hinges on implementing mandatory human-in-the-loop gates for any non-reversible actions, like financial transactions or infrastructure deployments. Without these safeguards, companies will remain hesitant to give autonomous systems the level of authority required to truly transform their business operations and efficiency. While the business potential for these agents is undeniable, the underlying technical debt in current frameworks might be creating a structural vulnerability that cannot be ignored. Vance, does the current state of agent permissions actually allow for the kind of security that these new federal guidelines are trying to mandate for the industry?
The technical reality is that many current agent frameworks are operating with permissions effectively equivalent to a change mode 777 command. This grants full file system access and unscoped application programming interface keys to the model, which makes regulatory compliance nearly impossible without a total and painful rewrite of the core permission models. We see this reflected in the Open Web Application Security Project Top 10 for Agentic Artificial Intelligence for 2026. They identify prompt injection and excessive agency as the primary vectors for system compromise. When an agent has too much power, a single malicious input can lead to a total environment takeover. Tools like Claw Mode have emerged as essential open-source middleware for sanitizing inputs, but they are only one piece of the puzzle. Outbound secret scanning is the only real defense against agents that might inadvertently leak environment files or secure shell keys while they are trying to solve a complex coding task. Securing these high-level autonomous workflows is a massive undertaking, but the industry is also looking at the literal silicon level to find improvements. We need to move from securing the agent environment to the hardware-level optimizations, making them faster, starting with TensorFlow 2.21 and LiteRT.
Google is making a definitive statement about the future of on-device intelligence by graduating Light Runtime to a full production-ready stack. By shifting core resources toward long-term stability and security fixes, they are signaling that mobile machine learning has moved far beyond the experimental phase into a primary business requirement for modern enterprises. The most compelling part of this shift is how it streamlines the developer experience across the entire industry ecosystem. By providing native model conversion for PyTorch and JAX, Google is effectively removing the massive friction that previously prevented teams from deploying their best research models directly onto consumer edge devices without expensive and time-consuming architectural rewrites. This level of cross-framework compatibility suggests a maturing market where the focus is finally shifting toward accessibility and scale. When companies can move seamlessly from a research environment to a production mobile application, the speed of innovation for consumer-facing generative tools on local hardware will likely accelerate at an unprecedented pace. Vance, when you look at the lower levels of this framework graduation, does the performance delta between the legacy systems and this new Light Runtime architecture actually justify the massive migration effort that Google is asking developers to undertake by the year 2026?
The performance metrics are actually quite startling when you dig into the hardware utilization. We are seeing a 1.4 times increase in graphics processing unit performance compared to the legacy TensorFlow Lite framework. This jump is critical for mobile deployment because it allows for much more efficient use of unified neural processing unit acceleration. Beyond raw speed, the expanded quantization support in version 2.21 is where the real engineering progress is happening. Introducing INT2 and INT4 data types for operators like the TensorFlow Lite fully connected, and slice functions is essential for fitting models like Gemma onto constrained mobile hardware without sacrificing accuracy. It is a massive technical hurdle to shrink these weights while maintaining the logic required for complex reasoning tasks. By prioritizing these specific mathematical operators, Google is giving developers a precise toolkit to optimize the memory footprint of their models. This ensures that the local execution of large language models is not just possible, but actually performant. These hardware-level optimizations are creating the necessary foundation for the next generation of massive multimodal systems. We are moving from simple edge inference to hosting sophisticated models like the Microsoft 5.4 Reasoning Vision 15 billion, which pushes the boundaries of how much math and visual reasoning a 15 billion parameter model can handle.
It is remarkable to see Microsoft achieving such high-performance benchmarks with only 200 billion tokens of training data. When you compare that to the 1 trillion tokens used for models like QN 2.5 or Gemma 3, it represents a massive leap in data efficiency for the entire industry. This efficiency is translating directly into practical capability, particularly with a score of 88.2 on ScreenSpot version 2. We are finally reaching a point where autonomous agents can reliably navigate complex software interfaces, which opens up incredible possibilities for automating legacy enterprise workflows that were previously manual. Beyond just navigation, the ability to interpret handwritten scientific equations and documents with an optical character recognition bench score of 76.0 shows a level of sophistication that is quite rare in models of this size. It suggests that 15 billion parameters might be a sweet spot for specialized multimodal tasks. Vance, looking at the underlying design, how does the integration of the sigmoid language image pre-training version 2 vision encoder change the way this specific model actually processes those dense image environments compared to the standard late fusion approaches we have seen in the past year throughout the industry?
The mid-fusion architecture is the real engine here, because it integrates the 5.4 reasoning language backbone directly with that sigmoid language image pre-training encoder. This specific design choice allows the model to maintain a much more nuanced understanding of visual context during the early stages of reasoning. By using a dynamic resolution encoder that supports up to 3,600 visual tokens, Microsoft is solving the problem of pixel loss in dense environments like graphical user interfaces. This high token count ensures that small icons or text elements are not blurred out when the model is trying to localize elements. We should also highlight that 20% mixture of reasoning content, which utilizes specific think and no-think tags to manage chain of thought logic. This structured approach to the training data is what enables the 15 billion parameter model to localize interface elements with such high precision and logic. While these architectural breakthroughs are pushing the limits of what a smaller open-weight model can achieve locally, the industry is still grappling with the massive overhead required to sustain these workflows at scale. We need to shift the focus from the technical model specifications to the hard financial costs of running these systems. Looking past those model architecture wins, we have to confront the hidden tax of the artificial intelligence era, which is the sheer cost of keeping an agent aware of its surroundings. When you have 6 agents running every 15 minutes on high-frequency schedules, the startup costs alone can spiral quickly. During the first quarter of 2026, these specific cron jobs were burning through $198 every single month just to initialize. That financial friction happens because context overhead for these agents reached over 8,400 tokens per hour per agent before any real work started. This is a massive red flag for any engineering team because it reveals a fundamental failure in how we handle state management architecture. If you are loading 2,100 tokens of data for every single run just to remind the system what happened 5 minutes ago, you are basically burning capital. The tiered initialization protocol addresses this by strictly categorizing files, but it requires discipline. If an engineer fails to prune that heartbeat file, The token bloat can exceed 500 tokens within a single week, recreating the very problem of recursive overhead we were trying to solve in the first place.
Vance, your warning about that maintenance burden highlights why the efficiency gains from this transition are so critical for the business bottom line. By replacing those 900 token memory files with a streamlined heartbeat file of only 150 tokens, we are seeing a dramatic shift in operational costs. The production data is staggering, showing a 76% reduction in total costs, which drops the daily context requirement from 432,000 tokens down to only 104,400. That kind of efficiency turns a money-losing automation into a high-margin asset. This tiered loading protocol changes the entire return on investment calculation for enterprise workflows because it proves that we do not need to feed the entire history into every request. It allows organizations to scale their autonomous networks without fearing a massive bill at the end of the month. When we find ways to prune the system so that it only loads what is relevant, like separating the core identity from the toolset, we unlock a new level of agility. It is this ability to optimize token costs that ultimately allows us to build entire platforms for the price of a dinner. We are witnessing a complete collapse of traditional development timelines when an individual can deploy a production-ready software as a service billing platform in just 12 hours. By utilizing an autonomous artificial intelligence agent, developer Volodymyr Saldin successfully generated over 10,000 lines of code for the project known as Billing Core. The financial barrier to entry has effectively evaporated when you consider that the entire build cycle cost approximately $150 in application programming interface tokens. This represents a seismic shift for startups because a fully functional system with 12 database tables is now achievable for the price of a standard business lunch. This level of velocity allows for rapid experimentation, where ideas are transformed into deployed services on Railway across 4 distinct production environments almost instantly. When the cost of failure is this low, the focus shifts from managing expensive engineering teams to orchestrating high-level autonomous workflows that can deliver complex architectures overnight. Vance, when you dig into the logs of this 12-hour sprint, what does it tell you about the technical maturity of these generated systems? It seems like a dream for a founder, but I suspect an architect might see some cracks in that foundation that the marketing numbers are not highlighting.
If you look past the speed, the logs show that the agent spent a significant amount of time refactoring over 30 RESTful endpoints from cookie-based authentication to bearer tokens. This was necessary to resolve cross-origin resource sharing failures, which proves that even advanced models still struggle with the initial configuration of complex security headers. The selection of Fastify for the backend and Prisma for the object relational mapping, combined with React 18, shows a preference for modern performance. However, managing 4 production services on Railway, including PostgreSQL and Redis, requires a level of environment synchronization that still feels like a significant hurdle for most autonomous systems. We are seeing the primary bottleneck in software development shift away from the actual writing of syntax toward the much harder task of infrastructure orchestration. While generating 10,000 lines of code is impressive, the true test for these autonomous agents is whether they can maintain state across a distributed system without constant human intervention. As we close out today, it is clear that security, efficiency, and velocity are converging in this 2026 landscape to redefine what it means to be a developer. The ability to manage these high-speed autonomous cycles will determine which platforms survive as we move toward a world of fully automated infrastructure. Our discussion today highlighted the extreme risks of the OpenClaw security breach, alongside the massive efficiency gains from tiered context loading, which dropped token costs by 76%, and reminded us that while you can build a software as a service platform for $150, the security debt might be much higher.
Vance, that tension between speed and safety is the defining challenge of 2026 as we move from experimental toys to production-grade autonomous systems, where every line of code carries both potential profit and significant liability. Because the objective now is ensuring these systems withstand the harsh realities of a live environment. As you integrate these autonomous workflows into your own infrastructure, consider whether you are prioritizing a quick deployment over long-term architectural stability before you leverage these tools that require a steady hand to guide them. And thank you for listening to the Dev Journal today, as we look forward to exploring the next frontier with you tomorrow.